we're going to look at the notion of derivative. And in order to do so, we're going to go through the notion of tangent to a graph at a given point. So imagine that you have the graph of a function. Here's the graph of a function. And we take a point on that graph. So to fix ideas, let's say that the function is f of x. So we denote the graph by y is equal to f of x. In other words, it consists of points whose coordinates are inputs and outputs for the specific function. And then imagine that we fix a point on the graph. So this point will look like a comma f of a, where a is some number. So here's the number a, and this will be the number f of a. Right? That's how we form the graph of a function, by taking all points where we juxtapose input and output. So now imagine that you ask somebody to perform the following task: to find a straight line that goes through the point a comma f of a and looks like the graph of the function as much as possible. Of course, this graph is not a straight line. So, when we say as much as possible, we mean close to the neighborhood of that point. So if somebody were to tell you that, look, this straight line looks very much like the graph of the function, your reaction would be, no, it doesn't. I mean, look, if we go very, very close to the point itself, then certainly this straight line, as straight as it can be in this drawing, of course, does not look anything like the graph. So, thanks for trying, but this doesn't work. Okay, so let's try again. So now let's do a much more serious attempt. And I think that this is a very, very nice attempt here. So sketching a line that looks very much like the graph when we move close to that point. Actually, the whole business of taking a tangent originates in the case of a circle. And we all know that it's, okay, this doesn't look like a circle, but let's give it another try. So if you have a circle and somebody gives you a point, it's easy to find the tangent to a point, to this point, the tangent to the circle at this point. In fact, the tangent is known to be perpendicular to the radius of the circle at that point. Okay, and in some sense, it does pretty much the same job. So if you look very, very close to that particular point where the tangent meets the circle, and if you want, you can magnify it, then you can see how the circle and the line look very, very being close to each other. And that's exactly what we're trying to achieve in this particular case. So, of course, there is a slight problem here. If you ask 10 people to draw what they think is the line that resembles the graph in the best possible way, you will most probably get 10 different answers. Okay, they're not going to coincide. But later on, we're going to see that there is a way, there is a very precise way to actually identify the one line that does the job. So, so that is going to be called the tangent to the graph at the given point a comma f of a. So this will be the tangent to the graph at the point a comma f of a. And in some sense, again, the main idea is that if we restrict our attention very, very close to that particular point, then that line is going to look very much like the graph itself. So if the graph is going up at that point, and when we say up, we mean as we look at it from the left to the right, which is the case with this particular graph at the point a comma f of a, then the tangent will also go up. Or if the graph is going down, then the tangent will go down. So somehow the tangent can be used as a means of describing the graph very, very close to that particular point. And after all, it's a line, so we know very well how to handle lines. In particular, maybe the single most important element of a line is its slope. So the slope of the tangent line to the graph at a given point is going to somehow give us a lot of information about how the graph of the function behaves at the given point. And for that reason, we're going to study it systematically. We're going to give it a name. We're going to call it the derivative or the derivative number of the function f of x at the point A. So the derivative number, and sometimes we will omit the number of f of x at A, will be denoted. It has a very interesting symbol, at least this is the symbol that we will currently introduce. You will see that later this might change. Will be denoted by f prime of A and equals the slope of the tangent to the graph of f of x at the point A comma f of A. I know it's a mouthful, but it's pretty much what we're going to work with, what we're going to devote a lot of attention to. So we're going to be working with the slope of the tangent to the graph at a given point. We're going to call it the derivative, and it's going to be a very important number for the function. By looking at the derivative of a function at a given point, we'll be able to actually do many, many interesting things. So let's now take a look at the equation itself. By using the point slope formula, we can actually find the equation of the tangent. So the equation of the tangent well, since the slope was denoted by this notation, f prime of A, the equation of the tangent is going to be, we're using the point slope formula, y minus f of A is equal to f prime of A times x minus A. So this will be the equation of the tangent to the graph at the given point. Okay, so to summarize, if f prime of A is greater than 0, then the graph of the function is going up at A. And when we say it's going up, we always mean as we look at it from the left to the right. And if f prime of A is less than 0, then the graph of f of x is going down. At A. Certainly one could ask what happens if the derivative is equal to 0. That's something that we'll want to discuss separately, and it's going to be something very, very interesting, actually. There is one case in which, even by what we know right now, we can compute derivatives very easily. That's when you have a straight line. So when you have a straight line, so let's say it's given by y is equal to mx plus b, somebody gives you a point on this line, you know, again, it's the point a comma ma plus b, and they ask you what is the derivative of the function at that point. Well, you know, ask yourself, what is the straight line that looks like a straight line very close to that point? And obviously the answer is the line itself. And what is the slope of the line? The slope of the line is m. So in this case, in the case that f of x is equal to mx plus b, you can argue that f prime of a is going to be m, and that's going to be for any number a. So this is a situation where we can compute the derivative very, very easily. In particular, if you have a line which is horizontal, so that would be a constant function, then its derivative, so if you have the function f of x equals c, then its derivative will be equal to 0 for all x's. Yeah. So that is a simple way of looking at the derivative of a function. So the derivative of a function is the slope. The derivative of a function at a given number is the slope of the tangent to the graph at the given point, the point that corresponds to that number. And that's all we have to say at this point about the derivative. Thank you for watching.